contents. So first of all, welcome back after the semester break, and I would like to synchronize everyone where we are in our 2-semester course sequence. And you do not have to copy that here. So just want to give you this overview again, this tree diagram, what we're going to do in the course, and give you a little bit of an idea what the big picture is. So, we know there's 3 big fields of modern cryptography. There are symmetric algorithms. Können wir leise sein? There's asymmetric algorithms, and there's protocols, whatever. And we define protocols pretty loosely, as you will see in a month or so. So we're done with symmetric algorithms. Actually, we've been done for quite a while. So we are right in the middle, as you will see, almost literally in the middle of asymmetric cryptography. What we did before the break is we did RSA. And I think I mentioned that before. There are only 3 families of public key crypto algorithms of practical relevance. One is RSA. The second one is exactly what we started the last week before the vacation, and that's discrete log crypto systems. Okay, and we're in the middle of that. And then the third family are elliptic curves, and where we are is exactly here. We're kind of in the middle. Coming down from here, we are halfway through discrete logarithm, so we're going to continue with that. And if this is the timeline, we're somewhere here, right? So this is the first semester, and this is the second semester. What we're going to do today, we finish discrete logarithm. Well, we do a second lecture on discrete logarithm. There's a lot to learn. It's cool. Next week we're going to do El-Gamal, so we're going to do encryption, actually data encryption with discrete logarithm. So we have 2 more weeks to go with discrete logarithm. Then we do elliptic curves, which is super cool, really cool, modern crypto system that's a little bit complicated, but also really cool. It's in all this BlackBerry type of modern sexy applications. They use elliptic curves. Really cool thing. So this is, and we're going to need 2 more weeks on that. So we have 1 today and 3 more weeks on these type of crypto systems. And then we're going over to protocols, whatever protocols are, things like digital signatures, hash functions, pretty much everything that's not symmetric or asymmetric. Okay? So again, you're here kind of in the beginning or middle of discrete logarithm crypto systems. It was the first thing to, synchronize ourselves. What did we do last week? And last week really means 2 months ago, right? What did we do last time we met? We did really 3 things. We introduced cyclic groups, all the stuff with order and primitive elements. We briefly introduced the discrete log problem. And I'm going to spell that out. If you don't know what DLP is, it's discrete log problem, but we're going to talk a lot about that today. And then thirdly, we did Diffie-Hellman key exchange. And what we're going to do today, essentially, we do similar things, but dig much, much deeper into that. Okay? So today we have actually 1, 2, 3, 4 proper chapters. First, I want to review what we did last time. In particular, I want to look at the discrete logarithm problem again. It's not complicated. This is like Diffie-Hellman. It's really it's not complicated. Okay. Then I want to look at the at Diffie-Hellman. It's a Diffie-Hellman problem, whatever that is. So this is somewhat new. It's a little bit abstract. Thirdly, and this is kind of the cool stuff to give you maybe a little bit an outlook. I mean, if you're wondering, isn't that exactly what we did last time? Yes, it is pretty close to what we did last time. One reason why we spend another week on that is the really nice thing about this discrete logarithm crypto system. That means the Diffie-Hellman type of crypto system. You can generalize them. This is like a general construction methods to build a lot of different crypto systems from. And in fact, even elliptic curves, which we classified as number 3, they're really only a generalization of here. So once you understood discrete logarithm, you have a really very beautiful tool set for building crypto systems. So it's pretty cool. And this is a little bit what's happening here. We talk about the generalized discrete logarithm problem. Okay. And then fourth, we do something which we rarely do in our course. We talk about attacks. Okay. Attacks are very, very important to understand, for instance, the difference between here and here. Or maybe I'll tell you that already to motivate you a little bit, to stay awake on Friday afternoon. Okay? So in order to get RSA secured, does anyone know what is the minimum key length, the minimum operand length for RSA? How many bits, roughly? 1,000. Very good. 1,000 is a very good answer. So let's say a little bit more technical, between 1024 and 2048. So this is what you like to see in your web browser. Okay? Not shorter. Discrete logarithm, long story made short, same bit length. We're going to talk about that later today. Okay? And now comes the cool stuff. You know, now it's getting really, really exciting. Elliptic curves you get secure with 160 bits. Up to, let's say, 256 bits. Okay? And why is that? Well, that has to do with the stuff we're doing today. Okay? And that's why BlackBerry has this elliptic curves in and not discrete logarithm. And who has an electronic passport already or elektronischer Personalausweis? Anybody here? You have elliptic curves in. And not RSA and discrete logarithm for that reason. 160, not 1024. That's the answer. So and again, it's pretty cool, and it's a little bit difficult to understand, and I'll try to explain that to you. Okay, so that was number 1. So let's start with the first chapter of today, and that's the review of the discrete logarithm problem, or DLP. So if you're wondering what DLP means up there, you know, on this blackboard, it means discrete logarithm problem. And let's start with the example, actually the same example we had last time. What we need for a discrete logarithm problem, we need a cyclic group. And we look at this group Z11 star. What is Z11 star? Well, it's this ensemble, the set, die Menge of 10 elements, except the 0. That's where we put the star here. So we have the elements 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay? That's not very deep. This is pretty straightforward. And now the beautiful thing about a cyclic group, does anyone remember that? Well, there's only one condition, actually, pretty simple condition. What is the condition to have a cyclic group? What do we need for that? We need one specific type of element, namely? It's a generator, exactly, a primitive element. As soon as you have a generator or a primitive element, that's the same thing, you have a cyclic group. And all these nice properties, you know, that you probably studied for the exam, only depend on this condition, do we have a generator? So, and we know if we build ZP, P a prime, so if you do modulo prime arithmetic, we have a cyclic group. Maybe let's write that down. So if we have a primitive element, that's the definition of a cyclic group. As soon as we have that, no, I'm sorry. Primitive element, what is the definition? That is the order of this element alpha must be the group cardinality. Okay, this is this funny symbol for number of elements in the group. Okay. Anyone recall how many elements do we have? I know we can count, but does anyone know? What is this? Which integer do I have to write down here? 10. Very good. Why not 11? What's missing? 0, right? We kick the 0 out. And it's always, if you have ZP, P a prime, the cardinality, the number of elements is always P minus 1. So if you have, what's another prime? 127 is a prime. If you have Z 127, you have 126 elements in the group. Okay, this is just the notation we're using here. So let's, maybe go back for a second to this notion of primitive element. What does it mean? It was just a very good remark here. I said, what kind of elements do we need to have a cyclic group? And he didn't say primitive element. He said, what was the other term for? There's another name for it. Generator, which is a better name. I mean, primitive element maybe sounds cooler, but generator is really more descriptive. Namely, it generates a group. So we look at alpha equals 2. And so we look at 2 raised to the first power, you get 2. 2 square, you get 4. 2 cube, you get 8. 2 to the fourth, you get 16. Modulo 11, you get 5. That's right, yeah. 2 to the fifth is 10. I continue here. 2 to the sixth is 20, is 9. 2 to the 7 is 18, modulo 11 is 7. 2 to the 8th is 14, modulo is 3. 2 to the 9th is 6. 2 to the 10 is 12, modulo 11 is 1. Okay? So if you go through the group here, if you look at the group elements, every single element that is in the group is a power of the primitive element, right? This is the only condition we have to fulfill in order to have a cyclic group. Okay, so one important consequence is now if you pick any elements better, any element in the group, what we know for sure is that this element beta can be expressed as alpha to the x modulo 11. Okay? This is clear, so if that's an example for discrete logarithm. The base, the primitive element is 2. The result is 9. What is x here? That's computing a logarithm. And what is the value of x here? Does anyone know? 6. How do we know that? Because we look up here, right? Okay, good. So, and now, again, this is all repetition, more or less, from last time. The definition of the discrete logarithm problem is as follows. Given P, an element beta in ZP, and a primitive element alpha, find X such that, ST such that, alpha raised to the X is equal to beta modulo P. Let's do another example, which is maybe not quite as trivial. That's still pretty easy. You know, move from 11 to 47. 47 is a prime, so we can use that. Beta is 41. And it turns out that alpha equals 5 is a primitive element. So the question is, what is X here, right? Which value do X? And this time we don't have this nice pre-computed table with all powers of 5, right? And does anyone have any idea?
42?
No. No, it's 41, but it's a good guess. Okay, so very good. So, no, 15, I'm sorry. 15, okay, I was wrong, 15, okay. So I just wanted to give you an idea, just by looking at it, it's not that easy to come up with a solution, and right now the best thing you can do is brute force, try X equal 1, 2, 3, 4, 5, blah, blah, blah. And there are better attacks, and that's chapter 4 of today. We talk about attacks. There are other attacks available. Right now we only have brute force, okay? So, that was all repetition from last week, and I hope everybody's on one page here so we know what's happening. And now kind of the fun part starts. Now we're going to, once we have this problem, and we already know how to build a crypto system for him, and now we look what we can do with it. So we're done with chapter number 1. That was pretty cheap today. So let's look at the next thing. We want to look at the big major, historically the first application of the discrete logarithm problem, that was Diffie-Hellman key exchange. So chapter number 2. Has to do with Diffie-Hellman. But we're not only talking about the Diffie-Hellman key exchange. That's what we did last time we met. We look at what's called the Diffie-Hellman problem. Very often abbreviated as DHP, okay? Well, if you want to look at the Diffie-Hellman problem, that probably has something to do with the Diffie-Hellman key exchange, and yeah, that's what we're going to do. So, recall Diffie-Hellman key exchange. And I don't know whether I told you that last time, but this is the most important protocol, okay? If I call you at 4 a.m. in the morning and I ask you Diffie-Hellman protocol, Diffie-Hellman key exchange, I want you to draw this picture, what I'm going to show you. Okay, so this must get burned into your brain till the rest of your life. Okay, till you get your bachelor degree here, okay, for two more years, okay. But so this is very, very important. Alice and Bob. We have alpha and p, which are often called the domain parameters, so it's shared by the whole community. This is much more than just a public key. This is shared by everyone. So we have alpha and p, which are somehow, it's on the web, it's in databases, everybody knows that. Okay, so Alice picks her private key, which we call lowercase a, car private Alice. Which is randomly picked from the set 2, 3, 4, blah, 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 up to p minus 2. Okay? And we're going to talk why we don't. You can actually include 1 and you can include p minus 1, but in practice they are kicked out, so we kick them out here too. Bob does the same. So Bob picks his private key Bob. Then Alice and Bob, each of them computes their own public key, which we denote here with uppercase letters. Uppercase A is Alice's public key, which is alpha to the A mod P. Bob does the same. So since these are public keys, they can be freely exchanged, right? They don't have to be kept secret. Alice and Bob, they exchange their keys. And now Alice computes B to the A. That means Alice takes a public key from Bob and raises this to her private power A. Mod P, of course. Bob, and this is a surprising thing, takes the public key he's getting from Alice and raises it to his secret power, B here. Modulo P. And the surprising thing is Alice and Bob compute the same secret. Okay? So this KAB is, in practice, is a 1024-bit number, and then what you can do, you take, let's say, the first 128 bits, the leading 128 bits, the MSB bits, and you use that as a key for your AES implementation. The other bits you don't need. Okay? That's the basic idea here. And again, we had that last lecture. Proof of correctness. Alice computes B to the A, right, and uppercase B. But what is B? Well, let's see where B is coming from. Well, B is coming from here. Bob computes B in this way here, so we simply substitute that. So we get this is alpha to the B to the A, so this is obviously alpha to the AB mod P. Bob computes, let's look what our friend Bob is doing. He's computing A to the B. Where's uppercase A coming from? Well, it's coming from here over the channel. And Alice computed her public key in this way, alpha to the lowercase a. Again, we substitute alpha to the lowercase a to the bth power. This is alpha a b modulo p. And that's it, right? Both parties, Alice and Bob, compute effectively alpha to the AB. This is the same number, same 1024-bit number in practice, or 2000-bit number. This proof of correctness is easy, okay? And we did that, and you know, there were even some exam problems on that, and now it's getting like a little bit interesting, because this is the easy part. I mean, this is showing that it works. What do you think are the other, what is the other requirement for a crypto system besides that it works, which is almost as important in cryptography? Yeah. Is it secure? I mean, I can, you know, I can come up with, you know, 20 protocols like that where Alice and Bob compute the same key. The hard question is it secure? And what does it mean being secure? What do we need here at this point? We need the bad guy, right? Can we break that? And who wants to break that? Well, probably Oscar, right? So our attacker model, and that's very important, now we define the attacker model, and we assume a very weak attacker. It means an attacker that observes the channel, but the attacker can only listen. So he's not what's called he's a passive attacker, he's not active attacker, he cannot manipulate. In about 2 months or so, in May, June-ish, we're going to talk a lot about what's going to happen if Oscar can manipulate the messages. If Oscar can fiddle around with AB, die Hölle ist los, right? Hell is loose here, okay? Really, things become really nasty. We need certificates, right? You know that your web browser comes up, certificate not accepted. This is what's happening here. Because if you have strong attackers, things become pretty nasty. But right now, we assume a weak Oscar. Oscar can only listen in. Oscar can eavesdrop. That's a fancy English term, eavesdropping, lauschen. Okay? So let's see now what happens with respect to security. Assumption. Oscar can only listen. Passive, right? This is a passive attacker. Active attacker is somebody who can manipulate messages. Okay? So, what does Oscar know? And I haven't used colors, for 30 minutes, so let's start with using colors. So what does Oscar know? And it turns out that Oscar knows a lot. He knows almost all the parameters of the protocol. He knows P, he knows alpha. These are domain parameters, right? That's one reason why I stressed that before. This is publicly known. Everybody knows that, okay? He knows, and now it's getting a little bit more critical, he knows his uppercase A, and he knows uppercase B, so he almost knows everything. So he knows alpha P, public key of Alice, public key of Bob, okay? What Oscar wants is, it's a good question, what does he want? What is the parameter he doesn't know and he would really, really like to know? Yeah. KEB, exactly. The ultimate goal here, and that's very important. What is this? And read from an Oscar's point of view, right? This is Oscar here. And if you can compute that, it's a stupid protocol, right? It doesn't work. Then, we can show that it's correct, that Alice and Bob can compute the session key, but if Oscar can compute the session key, it's not worth anything. So, what Oscar wants to know is KAB, which is alpha to the AB, okay? And this setup, this set of known and unknowns, this is called the Diffie-Hellman problem. Okay, having this set of parameters, that means having the domain parameters, having all the public keys in the system, but don't know the session key, the joint session key. This is what's called the Diffie-Hellman problem. So, how can he solve that? What would Oscar like to do in order to, what does Oscar have to do in order to compute a session key, KAB? Which parameter is missing here? Ja, da hinten. Lowercase, right? Klein a, klein b, ne? Genau. Entweder klein a oder klein b, lowercase a or lowercase b. That's the thing. So, 1 unterstrichen, fett, ja, rot, highlighted, 1 way of solving the Diffie-Hellman problem is along the lines what the colleague just told us. Compute lowercase a, let's say, or lowercase b. It's a symmetric. It doesn't matter which one. So the first step compute lowercase a. And from which parameter do we compute lowercase a? In which parameter is lowercase a contained here? What do you guess? Not in P, right? Yeah. Any ideas? Yeah. Big A, exactly. Uppercase A. And how? Well, it's somewhere. Where was that? Here. Uppercase A contains lowercase a. So if you have uppercase A, what do we have to do? What is this operation called here to extract the exponent? 9. Klasse. Mein Sohn Noah hat gerade Klassenarbeit darüber geschrieben. Das ist ein Logarithmus. This is a logarithm, right? You have to compute the logarithm. Unfortunately, it's not the logarithm that my son Noah just did in ninth grade with his pocket calculator. It's the discrete logarithm, right? So it's logarithm to the base alpha mod p and all this nice stuff that you learn in engineering calculus, in engineering mathematics doesn't work here, right? So, but if it works, if you can compute A, it's great, because once you have the private key, Oscar computes, now it's easy because he has the private key of Alice, so he knows everything that Alice knows, and he can do this step here, right? He takes b to the 8th power, and he computes KAB, which is alpha A B mod P. Okay, so that's it. So we know how to solve the Diffie-Hellman problem, and where is the problem with that? Why is it not so easy in practice? Which of the two steps is hard? Just told you. The first one, right? This is one way of solving that, right? And it looks pretty nice. It has this little drawbacks that Oscar cannot do step number 1 here. Okay? So, but now comes kind of the important discussion that follows from that. Okay, so unfortunately, for Oscar, I should say. Okay. Fortunately for your web browser, right? Unfortunately, from an attacker's point of view, I'm cynical here. Okay. Unfortunately, step 1 is computationally a very hard problem if P is large enough compared to section 4, chapter 4 of today, right? With our laundry list for today here. We're going to talk about attacks, and then we talk about what we mean with large. A rough idea I gave you already, 1024 bits. Okay, so P has to be large. Actually, there are a few other conditions you have to be careful. Also with picking alpha, you have to be a little bit careful, but it's not super hard, okay? So that's the first statement, okay? So, and now comes kind of a theoretical cryptographic foundation type of statement, stuff we usually don't do, and you have to wake up a little bit. You know, people always say it's really good that you wake us up, and that's what I'm doing now. Wake up, stop talking. Now comes a very simple statement. Just try to understand what that means is what people in cryptographic foundations, so the basics, the modern theoretical basics of cryptography talk a lot about is, okay, so what we really want to do is we want to solve this problem, right? Oscar wants to have the session key, okay? Well, we kind of know how to do that. We have to solve the discrete logarithm problem. This is also clear, right? When you solve the discrete logarithm problem, you can get the session key. So what people on the in cryptographic foundation are very interested in is this the only way? That means in order to compute KAB, do we have to compute the discrete logarithm? You know, that means step 1 and then step 2, or is there a different step 1? Seems kind of a little weird, but it's not clear that you have to solve the discrete logarithm problem to get this here, okay? And that's the difference between the Diffie-Hellman problem and this here is the discrete logarithm problem. Okay? So that's kind of a very important relationship between those two problems, and I want to write that down. If, zweimal unterstrichen, if the only way of solving the Diffie-Hellman problem, DHP, the only way of solving requires the discrete logarithm problem, really the solving of the discrete logarithm problem, comma, one would say, das heißt, man würde sagen, one would say that in quotation marks, in Gänsefüßchen, the Diffie-Hellman problem is equivalent to the DLP. They're essentially the same problems, okay? However, this is not proven und in Klammern yet. Das ist noch nicht bewiesen. Okay, people are working on that. If you want to become really famous, you prove that. Okay, it's very difficult. Big, very smart people, much smarter than I, tried and haven't succeeded yet. Okay, you don't become super famous. You just become famous in cryptography. Okay. From a practical crypto point of view, you know, 2 semesters in an engineering program, IT security, this is not that super important, but later on you will get lectures in more like pure modern theoretical cryptography, and this is all they're talking about. There will be very little doing stupid little toy examples by hand, and a lot looking at these type of problems and trying to prove them or proving these type of problems. So it's just, I want to give you a little bit idea what modern cryptographic research is about, okay? Maybe I go one addition here, which actually is maybe, which is probably of more practical relevance. So with discrete logarithm problems, they're pretty strong theoretical indications that these 2 problems are in fact equivalent. That means the only way of computing the Diffie-Hellman problem requires solving the DLP. This is very different in the case of RSA. Okay? In the case of RSA, the situation is similar. Doppelpunkt. What is the main attack against RSA? What do we have to do to break RSA in practice? Factorization. But here it's even more extreme. This is from a theoretical point of view, this is absolutely not clear that this is the best possible attack or the only attack. Right now we don't know any better attack, but this is if you go back in our textbook, you'll see that we don't really have to factor. We have to compute a Euler's phi function, and it's not clear that this really requires factoring. Okay. Factoring is not necessarily the only way to break RSA. It's just the best thing we know today. That's why people talk about factoring. And actually there's a few, big prominent crypto people and number theorists, they say, well, there should be a better way. Gut. So that was, kind of a little bit, again, this is a little bit introduction to modern, what modern proof-based cryptography deals with, what kind of problems. And we do the foundations. This is very important that you understand all the crypto systems. That's what we do in this course. And then in, the follow-up course in theoretical cryptography by Professor Mai, you understood them and you do more and more examples with that and you do practical protocols. And then I think from a pedagogical point, it's really good. And then in a year or 2 years, you step back and you say, what is really at the very root of this problem? What can we do in principle? And this is this type of stuff. So what we want to do now, and I think it's getting more and more interesting, that lecture today. So now we want to look at generalizing this problem. Okay? This, again, I told you right now, this seems like, where's Diffie-Hellman? This looks like kind of a funny protocol, pretty simple and cool. You can compute a session key over an unsecured channel, but it seems rather specific. What I'm going to show you now is how to starting to generalize that and essentially staying with the same protocol. We're not stuck with modulo p arithmetic. You can do different things, including, elliptic curves, which is super wild, right? It's very wild. Has nothing to do with modulo p arithmetic here. Okay? So this is the third chapter of today is the generalized verallgemeinertes generalized discrete logarithm problem. So people who really like abbreviations right? Abkürzungen GDLP. Okay. I don't know how often that is used, but you could use it. One powerful feature of the discrete logarithm, one thing that is really cool is not restricted to ZP star, ZP star, but other cyclic groups can also be used for building DL cryptosystems. That means if you ever what was that here? Let's say we have a group, but this time it's a general group. It's cyclic. Cyclic means, that was my question at the very beginning. When is a group cyclic, what do we need for that? There's only one thing we need, namely, I'm not continuing. What do we need for a cyclic group? Primitive element. So we have alpha, and now you'll see this is kind of a cool way of writing that. You can write all group elements also as a power of alpha, right? Alpha 2, alpha cube. And the last one is actually it was Fermat's theorem. We did that last time. Okay. Alpha to the g is equal to 1 here. Okay. So alpha is primitive element. Okay. That means, again, you have alpha, alpha square, alpha cube. Okay, exactly what we had before, but this time it doesn't have to be ZP. It can be any cyclic group. Okay, and now once we have that, we can define the generalized discrete logarithm problem. DLP is as follows: given cyclic group G, this notation, you have to watch out. Yeah, wake up. 30 seconds, I promise. It's for the homework assignment. If you write G comma something, like G comma plus, what this means, it's a group, the group operation is plus. If it's G comma times mal, it's a multiplicative group. And what we do here, if you do donut, right, little circle, kleiner Kreis, okay, Berliner, okay, it means it's either additive or multiplicative, okay? Given cyclic group G with this operation donut, okay, and this group order, this group cardinality, the number of elements are denoted by lowercase n. Let alpha be primitive element and beta is in G. Now, find x such that, I abbreviate that with ST. Now find an integer x with the following property. Ultimately, we want to compute beta, right? Or beta must be the result of some computation. So what we do, you take alpha, you apply the group operation, and right now it's a little donut. We don't know whether it's additive or multiplicative. Times alpha, blah, 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 blah. Times alpha. And how often do we do that? How many times do we do that here? What do I have to write? How many alphas do I have here? This is x. X is the counter of how often do I do the group operation here. So this is... We had that before. It wasn't that confusing. Where is that? Here. You know what this, if I write alpha to the x, what this really is alpha times alpha times alpha x times, right? That's what I'm doing here. Just right now, I don't want to say whether it's multiplicative or additive. And why do I keep talking about donuts? You will see, because the notation changes quite dramatically. Namely, if the group operation is multiplication, which is exactly what's happening here, right? It's alpha times alpha modulo p, it's times. Then we say, well, this is alpha to the x, okay? If donut denotes multiplication, okay? Now my question is, what about the other case if this is additive, if this is alpha plus alpha plus alpha plus alpha, what is the notation here? What do I have to write down here? X times. Yeah, you still think that's funny, but... And I can tell you where the confusion is. And this is going to come in 2 weeks when we do elliptic curves. Elliptic curves, you don't do alpha times alpha, you do alpha plus alpha. The problem is, I can tell you what it is. Up to here you think, big whoops, this is exactly what we did before. But then later on in the protocols, you don't see alpha times alpha times alpha. Where's the protocol? Where's Diffie-Hellman? Here. Diffie-Hellman, you say alpha to the p, then in elliptic curves, what you suddenly see, you see a times alpha, you say, oh, this is a really boring multiplication, okay? And it looks really easy, but it's really more like an exponentiation with, square and multiply, and there are a lot of really things involved. This looks too benign, too harmless, okay? There's a really bad one-way function behind that. It's often confusing. We always... in the exams, people really get that wrong a lot, okay? But that's what and it's just a question of notation. So if this becomes plus here, this looks pretty harmless. It's not very harmless, okay? Just be warned, okay? So, the cool thing is, and we should probably provide a frame, I would even use a red for this here. The cool thing is here, what I told you is, you can do for Diffie-Hellman, you do not necessarily have to do the thing with integers modulo p arithmetic. You can use other cyclic groups, and there are other cyclic groups on planet Earth, right? So now question at this point here, maybe write that down here. Question. Which other cyclic groups make good DL problems? And again, as soon we have a discrete logarithm problem, you can apply the same protocol. You can do Diffie-Hellman, but then maybe not do integer arithmetic. Maybe do something very, very different. And what I'm going to show you now, I mean, this is just Faktenwissen, factual knowledge. This is pretty hard to get somewhere else. There are very few good kind of description. What I'm going to show you the next 2 minutes. It's not complicated. It's just factual knowledge. It's hard to get. So be aware. Be awake. So the most popular thing that people do if they want to build discrete logarithm problems, so Diffie-Hellman type of protocols, they do what we've did so far. They actually use CP star, okay? That means what is that in mathematical terms, the cyclic groups that we're using, that's the multiplicative group of a prime field. Do you remember AES and we did finite fields? Week number 5 or 6 of the course in November. This is what that is in mathematical terms, okay? You have ZP, you know, ZP is a finite field, a prime field, and then we only look at the multiplicative part of that. So this is super widely used in practice. It's in your web browser, okay? What you can also do is, for AES, we didn't use a prime field. What kind of field is being used for the advanced encryption standard? Does anyone know how that is called? This French Galois field, exactly. So what you can also use is GF2 to the M, and again, you have to kick the 0 out, so star. You know, all these polynomials except the 0 polynomial, okay? So what is that algebraically? That's a multiplicative group of a extension field. Extension, Erweiterungskörper because of this M here, okay? And actually, you can also use GFP to the M, but in practice, people only use GF2 to the M. And people don't use this often for whatever reason, okay? So now it's getting interesting. The third thing are elliptic curves. What is the group here? And again, we have to talk about that we're going to spend 2 weeks on that. This is just getting ready. Kleine Vorwarnung. The group consists of points on a curve. It's like analytische Geometrie, stuff you do in 10th grade or so when you look at the circle equation or an ellipse or an oval, these. What kind of thing is this here? Anyone know this equation here? Circle, right? Kreis. So we look at these type of equations. So it seems completely different from crypto Diffie-Hellman. It turns out you can use similar things for building crypto systems. Okay. So that's this is compare. And again, I think super cool. It's kind of the coolest part of the whole lecture. Okay, but you have to wait 2 more weeks. Okay, and this is super widely used in practice here. Let's say in the old days there was only RSA and Diffie-Hellman, and then in mid-80s they proposed elliptic curves, Neil Koplitz and Victor Miller. In the beginning they thought this is just esoteric, very weird mathematics, it's too slow and too complicated, blah, blah, blah. And then people did a lot of research for 15 years, including my group in the US back then. And, and 15 years later people said, oh, we were wrong. This is really much faster. So, and this is state of the art. It's smaller and faster, and that's why a lot of this new sexy application, BlackBerry, actually using elliptic curves. Okay, so this used to be kind of a very exotic scheme. Now it's a very much mainstream scheme. And fourth is generalizations of 3, e.g. zum Beispiel hyper-elliptic curves. Okay, and this is exotic. So what's being used in practice are these two. Okay. And again, this is what we did last week, and we're doing today, and we're going to do next week. And then this comes after. So we do the 2 big practical things here. Okay, so this finishes the 3rd section of today. And now we already come to the last chapter, namely, we talk about attacks. And when we talk about attacks, we have to look at this, what we have here. Okay. Attacks against the DLP. Yeah, and I can tell you why do we talk about attacks here, because if you have a powerful attack, you will see we need really long bit lengths. If the attacks are really poor, if Oscar doesn't have powerful algorithms, we can choose smaller parameters and we probably get faster crypto systems. And this really, where was that? I'm going to explain these a little bit. I give you somewhat of a reasoning where are these different bit lengths coming from. Okay, so this is why I put that in an extra chapter. And again, it's kind of difficult to find in the literature in an easy way. So what we want to do as an attacker, as an Oscar, we want to compute a discrete logarithm in this way here. Okay? And the parameters are as always alpha and beta ing. And this group cardinality is n, and n is going to become important now. How many elements do we have here? Okay, So what are the attacks? First attack is brute force. It's a nice thing. It's a really dumb attack. We don't have to think much. Okay. So what we want to have, maybe let's also rephrase that here. Alpha to the x is better. We know that an x does exist. And x, I should have said that before. What type of thing is this x here? What kind of data type, if you wish? Again, louder. Yeah, the Ganzzahl. X is always an integer. X is simply counting, I'm multiplying or I'm adding 1 times, 3 times, 5 times. So alpha is always an integer. It's not clear that alpha and beta are always an integer, okay? In this case that we're considering, and kind of from a pedagogical point of view, it's really bad. Because the group elements are integers, and this exponent is that, okay? What about GF2 to the m? What are the group elements here? No, not functions, but almost. Polynomials, right? Here the group elements are polynomials. Is x a polynomial if we use a Galois field here? No. No, it just counts how often we multiply. Elliptic curves, again, we're doing that in 2 weeks. What are the elements? Wild. Really crazy points on a curve, blah, 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 blah. So it has nothing to do with just an integer. So here the group elements are weird things. Hyperelliptic curves it's insane, okay? It's verrückt, okay? So the group elements are really crazy. X is never crazy. X is just eine ganze Zahl. Very nice, brav, well behaved, okay? So bear that in mind. So now, we have to find this well-behaved x. Okay, so what we can do is, well, you simply try all possible x's, right? You check if I raise alpha to the first power, which is not that difficult, is this actually better? Probably not. You try the next one, and so forth. Okay. How many steps do I have to perform in the worst case here? What's the worst thing that can happen with this notation here? N, right? Because there are n elements in the group. So if you're going to get that in discrete mathematics, this is a große O-Notation, big O notation. So the complexity is big O of n steps. Okay? Yeah.
N-1 because...
Ja, no. Es ist n minus 1, ich mache das in Deutsch, aber das steckt in dieser Groß-O-Notation. Die Groß-O-Notation, die lässt all diese kleinen Konstanten wegfallen. Und wenn wir den Durchschnittfall zum Beispiel haben, was wäre der Durchschnitt hier? Also n Elemente wäre ja extrem, wir würden alles durchhalten und der allerletzte ist es. Ne? Das wäre genauso ein Extremfall wie der erste. Ne? Und im Durchschnitt brauchen wir wie viele? N halbe, ne? Wenn sie 1000 Mal machen, sind sie so, im Schnitt liegen sie genau in der Mitte hier, ne? Irgendwie bei, Sie kennen im Moment diese Groß-O-Notation nicht, die kommt noch. Groß-O-Notation, Big O-Notation says drop all these little constant kind of things, okay? So would that be good or bad? Well, that would, from a web browser point of view, if we are the good guys, if we Alice and Bob, that would be fantastic. If the only thing that Oscar could do is try, in a very stupid way. Okay? So if this were the case, if this is the only attack, if this were the only attack, how large do we have to, that's what we really want to talk about, how big is this group that we need here? Well, it turns out to Did anyone remember DES? How many key bits are in DES? 56, right? And 56, you know, with the Copacabana we can do, and it's not super easy, but it can be done. So what to say, kind of the lower threshold, you know, which is you cannot do with today's computers 80 bits. So if this were the only attack, we would say, okay, n, that means the number of elements in the group size is at least 2 to the 80, okay? And why do we say that? Well, if you want to attack that, you have to do something around 2 to the 80 steps. You cannot do that today. You can probably do that in 15 or 20 years. Right now, it's pretty hard. Okay. So that was attack number 1. Now we look at second, which are the so-called square root attacks, Quadratwurzelattacken-Angriffe, okay? And so we immediately, there are 2 attacks, okay? There's the one has a very pretty name, baby step. Giant step, auf Deutsch, Babyschritt, Riesenschritt, baby step, giant step. There's also another name which is not as nice, okay? Baby step, giant step, and algorithm. And Pollard's row method. So there are 2 attacks, okay. Compute x in. Before, brute force attack computes x in n steps, right, on average. Yeah, about n steps. So, well, they are called square root attacks because they use square root n steps. Okay. What are the consequences? And these attacks are they're very easy. Okay. And we haven't, if you don't know what the attacks are, you're absolutely right. We don't do them in this course. Okay, but they're not complicated. So, what follows from that, and the only thing we need to know, they're attacks, they're not really complicated, there's square root complexity. So, if n is, let's say, approximately 2 to the 80, which was the minimum requirement to be resistant against brute force attacks, if you do, and you can do that here, but the new attacks that are just not introduced, but I told them that they exist, right? You take these attacks, and instead of 2 to the 80, you have square root of 2 to the 80. Which is 2 to the 40. And this you can do on your laptop. Okay? Your laptop can do between 2 to the 40, 2 to the 50 things. Okay? Loops of iteration with a little bit of computation. You can do that, I don't know, and depending on the details what you have to do in every step, but you can probably do that in a few minutes on a standard, whatever, 2 gigahertz Intel laptop. Okay? This is bad. Okay? That means 80 bits is too short because there are better attacks out there. So my question now for you is, so here we reduced 80 bits to a 40-bit complexity, so to speak. In order to have an 80-bit security, what do we have to do? How long do we have to choose that here? What do you think? To be to have the same strength, to have this 80-bit strength here with these attacks. How long do we have to choose the group here? Yeah? 160, exactly. If n, that means if you have 2 to the 160 group elements, that means the group is represented by 160-bit numbers. We can attack it. We can use the more powerful methods here, but the best thing we can achieve is still that the attacker needs 2 to the 80 steps, and you can do that with your pocket calculator, even if one step takes only 1 picoseconds. 2 to the 80 picoseconds is still, I don't know, 1,000 years or something. Okay, and this is exactly the reason why elliptic curves have at least 160 bits. And why is that? Because for elliptic curves, these are the best possible attacks. For elliptic curves, this is the best thing you can do. Okay, now comes a very important statement about these attacks. Okay. Important. Square root attacks work in any for elliptic curves, they are the best known attacks. Okay? And again, this is just factual knowledge. People don't usually say that clearly, and this is why the German national ID card, the Personalausweis, has elliptic curves in it, because these are the best attacks. So, more details. And this is, more details. I didn't give any details about attacks. So if you want to learn about the attack, more details. On the attack, this is, my favorite crypto reference books. This is the Handbook of Applied Cryptography. Okay, hack. You can Google that as hack. And this is algorithm 3.56, which is baby step, giant step, and algorithm 3.60. The nice thing, this book, and I'm sure I mentioned that earlier, you find on the web by the author for download as PDF. Okay, so chapter number 3. It takes you about 2 hours, I would say, on Sunday afternoon to understand the attack. If you're really interested, ask me, maybe not today, but ask me next week, or ask during the Übung. Okay, we can. It's not that super complicated. So, but if you want to understand, then do that. So now we come to the end of the lecture. And actually, I do, because we end a little bit early today. I switch to German. Wir haben hier eine Umfrage. Die brauchen ungefähr 2 Minuten, die auszufüllen. Ja, ist also kein Problem am Freitagnachmittag. Das ist nur, halten Sie sich fest, nur für die Leute, die im 2. Semester ITS studieren. Bachelor. Wer ist Bachelor ITS 2. Semester? Fast alle. Wer ist es nicht? Sie füllen die nicht aus, okay? Sonst machen Sie die ganze Statistik kaputt, okay? So. Nein, Sie bleiben noch hier. Ich mache noch 5 Minuten Vorlesung, ja? Okay. Hier ist der Deal. Ich mache jetzt noch einen kleinen Fakt. Ich teile die schon mal aus. Warten Sie, bis ich fertig bin mit dem Ausfüllen. Das geht ratzfatz in 2 Minuten, ja? Okay. Jeder nur ein Kreuz, ja? Leben des Brian. Nee, jeder nur ein Blatt, ja? Und nur die Bachelor, okay? Okay, back to the lecture. So we had the dumb attacks, brute force attacks. We have square root attacks, which always work, and they're not that super powerful. You know, you get it with 160-bit, you get a secure system. So people that really paid attention here is, why in the world do we have to go to 1,000 bits here? Okay, and this has to do with the third subsection here, the third type of attacks. And these are kind of the super attacks. Third are index calculus attack. Okay, what is that? Remember, you probably notice this red box here, right? So this was for any group, for any discrete logarithm system, these square root attacks work, including elliptic curves. Here, there are super powerful attacks out, which are called index calculus. It's a whole family of attacks. But they only work against certain type of discrete logarithm problems. So they're not general attacks. They're only specific to, this crypto system. For certain groups, G, the more powerful index calculus exists, okay. In particular, the attack works remember I showed you the cyclic groups people have been using, in particular against the first two ones, okay? The attack in particular, also im Speziellen, besonders in ZP Stern, ZP star, and GF2 to the M. It means the stuff that is in your web browser, because most web browsers actually don't have elliptic curves built in. They still do the classical Diffie-Hellman modulo P. What does this mean? We have a most powerful attack. More powerful attack means, for instance, if you would do this Diffie-Hellman, where is this here? Where's the protocol? Okay. You can do this protocol with 160-bit numbers. And people did that actually. There was one commercial product, I think by DEC, the old computer company, DEC. I think there's some story. They used the 128-bit or so Diffie-Hellman key exchange, for securing computer communication or early forms of computer networks, because they only knew about the square root attacks. And then index calculus attack came along, and it turns out you can break them. And same situation now. If you would do that with 160-bit prime numbers here, you could, you learn how the attack works. You can easily break 160-bit, very, very easily break with your laptop. Okay? So in order to prevent you from breaking, other people's Diffie-Hellman systems, we have to choose larger primes. Okay? In practice, P and 2 to the M have to be much, much larger, unfortunately, than 160 bits. So what people say nowadays, at least 1024 bits, and then finally I can use my book here. Wette 2 zu 4. And I'll This is kind of an... And people have been trying that. You know, people tried to break discrete logarithm problem. This is a pretty small table. I'll blow that up for you. Is it readable? Yeah. Okay. Okay, this is... do you see the middle one, the bit length? So these are the records, you know, Weltrekorde in computing discrete logarithms modulo p here. Okay? And you see the last thing that was broken was in the year 2007, and people broke discrete logarithm problem with 532 bits. Okay? And I have to say, relatively, there are fewer people are interested in that than in doing RSA. So probably intelligence agencies, you know, NSA type of organizations, or the British intelligence organization, they can probably do a few hundred bits more. Okay, and that's why they say we have to at least go to 1,000 bits. And what's very common, so you need at least 1024 because you see the record is coming 532. I assume the research community could do 600 bits, 650 bits if they really wanted to. And then, you know, intelligence agencies probably can do a little bit more with more computer power and maybe somewhat better algorithms. So in practice, often P is in the range of 1024 2048 bits. Okay, this is what people very, very often do. So a lot of web browsers, if they're configured, is anyone using PGP here? I'm using PGP. For instance, this is, you know, if people ask which parameter you can, if you can configure that, people should say 2,000 bits if you want to have a little bit of long-term security. Okay, so that seems pretty secure. Again, we're definitely not doing index calculus here. Before I told you the other two algorithms, they're not that difficult. This is Sunday afternoon. Index calculus get a little bit more involved. Again, the best reference is also in the Handbook of Applied Cryptography. And they have a nice toy example in there, and it's algorithms, chapter 3, algorithm number 68. Okay. Are there any questions? Ja, Montag ist die erste Übung. Any more questions? Okay, so when you came down, could you maybe put the ausgefüllte Fragebogen on here? Thank you very much.